Hi there. We're going to go through problem 31b. It has a lot of parts to it, so I thought I would do a video just on this one. So we have to think about a few things at the beginning before we even start. So if I have if I have the integral of the quantity f of x plus g of x dx, I can split that into two, the integral of f of x dx plus the integral of g of x dx. Then one of the rules from our integral sheet, if they have the integral of e to the ax dx, that's equal to 1 over a e to the ax plus c. If I have the integral of x e to the ax dx, that integrates to e to the ax over a squared times the quantity ax minus 1 plus c. So if we're doing our evaluation of our integrals and we end up with a situation where we have e to the minus infinity, that's equal to 0. If we have e to the 0, that's equal to 1. Okay, so we have e, and the opposite action of the exponential function, or I should say the e function, is the natural log, or ln. So if I take ln of e of x, the ln is undoing what the e does, so I end up with x. The ln of 1 is 0, and the ln of a over b is equal to ln of a minus ln of b. And we're going to use all these in this problem. So let's start. Our first goal is to get the expected value of the absolute value of x minus a. And this is running off of an exponential probability distribution. So we have the integral from 0 to a of a minus x times the exponential distribution dx, plus the integral from a to infinity of x minus a times the exponential probability distribution dx. So what I'm going to do is take these two integrals and split them into 4 parts. I'll have the integral from 0 to a of a times the exponential dx, then minus the second piece, which is coming from this line, minus integral of 0 to a of x times the exponential dx, plus, then we're going to the second piece here, the integral of a to infinity of x times the exponential dx. And finally, we're going to subtract out the integral of a going from, or the integral going from a to infinity of a times exponential dx. So we're going to integrate each part and then put all the parts together. So we have a lambda e to the minus lambda x dx. The a and the lambda are just constants, so I can move them to the left of the integral without hurting anything. There's no x's involved there. So now I have the integral going from 0 to a of e to the minus lambda x dx. And I'm going to write that as a times lambda. And when I go back to my rule that I had a couple minutes ago, this is going to be e to the minus lambda x over minus lambda. And we're going to evaluate that from a to 0. But I can cancel those lambdas right here, and that's going to leave me with minus a times e to the minus lambda, and I'm going to evaluate that from a to 0. So I'm going to end up with minus a times e to the minus lambda a minus 1, because I had e to the 0 here, so that's a 1. And when I multiply through by the minus a, I get minus a times e to the minus lambda minus a minus a, or a minus a times e to the minus lambda a. So that's our first term, and I gave that 1 star. You'll see each part's going to have its own number of stars. So we're going to have the second part is minus integral going from 0 to a of x times the exponential. But I can pull that lambda out again. So now I have minus lambda of the integral going from 0 to a of x e to the minus lambda x dx. But here again, that's one of those formulas that's up on the first part of the page. So we're going to have minus lambda times e to the minus lambda x over lambda squared times the quantity minus lambda x minus 1 and evaluated from a to 0. But I can cancel a lambda out of here. So I have minus this whole bracketed term e to the minus lambda x over lambda times the quantity minus lambda x minus 1. And I'm evaluating that from a to 0. And we're going to have, when I do the evaluation, I'm going to have e to the minus lambda a over lambda times minus lambda a minus 1 minus e to the 0 over lambda times the quantity 0 minus 1. Okay? So then when I go ahead and multiply my minus sign through, it changes the signs here. This becomes a positive, but I still have a minus value here. So I'm going to end up with e to the minus lambda over lambda times lambda a plus 1 minus 1 over lambda. And when I go ahead and multiply through, I'm going to have, from the first term, the lambdas cancel. So I have a e to the minus lambda a plus e to the minus lambda a over lambda minus 1 over lambda. And that's my second piece. Okay, so let's go on to the third one. So here we have the x times the exponential again, but this time we're evaluating from a to infinity. So I'm going to pull the lambda out like we did before. I still have the same kind of term here. I have lambda times the bracketed term of e to the minus lambda x lambda squared times minus lambda x minus 1 evaluated from 0 to a. And what I'm going to do is cancel that lambda, one of the lambdas out. So now I have e to the minus lambda x over lambda times minus lambda x minus 1 evaluated from infinity to a. So the first term is just going to go to 0 because I'm going to have the e to the minus infinity goes to 0. This whole term goes to 0. And it's going to cancel out the first one. So we have 0. And then when I evaluate at a, I have e to the minus lambda a over lambda times the quantity minus lambda a minus 1. And when I multiply through, I end up with e to the minus lambda a over lambda times the quantity lambda a plus 1. And when I go ahead and multiply out, the lambdas cancel in the first term. So I have ae to the minus lambda a plus e to the minus lambda a over lambda. So that's my third term. So my last term, I'm evaluating from a to positive infinity. I have a lambda e to the minus lambda x. So I pull the I have the minus on the outside already. I have a times lambda, and I'm going to have the integral going from a to positive infinity of x, my fault, e to the minus lambda x dx. But here again, that's one of our rules. So we just plug that in. So I have e to the minus lambda x over minus lambda. The minus signs cancel, the lambdas cancel. So I'm evaluating e to the minus lambda x going from positive infinity to a. The first term is going to go to 0 again because I'm going to have e to the minus infinity. Then I'll have minus ae to the minus lambda. And so my final term will be minus ae to the minus lambda a. All right, so there's our 4 terms. Now what I'm going to do is combine all those ones that have those little stars. So I started from the 4th one and worked backwards. So as you see, the first 2 are going to cancel each other out. I've got e to the minus lambda a over lambda. I've got another one of those, so that goes to 2. This term, the ae to the minus lambda, minus the last term, that cancels each other out. And I have minus 1 over lambda plus a. So now I'm looking for the minimum value of a for this problem. So I'm going to take the derivative with respect to a of a plus 2e to the minus lambda a over lambda minus 1 over lambda. So when I take the derivative of the first term, it just goes to 1. The second term, I'm going to pull out the constant, the 2 over lambda, and then I'm going to have e to the minus lambda times the derivative of minus lambda a, which is just minus lambda. The last term, since there are no a's in it, it just goes to 0, so I don't have to worry about it. So I'm going to set that derivative equal to 0. So I have 1 plus 2 over lambda times minus lambda e to the minus lambda a equals 0. The first term still stays at 1. I'm going to cancel the lambdas out of here, and I have minus 2e to the minus lambda a equals 0. I'm going to add 2e to the minus lambda a to both sides, so I end up with 1 equal to 2e to the minus lambda a. I divide both sides through by 2, and I end up with 1/2 e to the minus lambda a. And remember, I want to solve for a. So I'm going to take the log of both sides. So I really have the log of 1 minus the log of 2. These are natural logs, but the log of 1 is just 0. So that term drops out. I have minus log of 2 equal to minus lambda a, and I divide both sides through by minus lambda, and I end up with, that should be log of 2 over lambda. Okay? All right, that's how you do it. Hope you liked it.